topic for today will be transport with fluid and solids. Transport including fluid and solid reactions. So a couple of weeks ago we started with reaction kinetics, and we saw how to go about think about that and doing that. We're really going to expand on that now and include include basically a focus on reactions that involve interactions between fluids and solids. So here are just some examples. This is ion exchange resin, these beads, and so this is used for water softening and other water treatment processes. And basically you have some solid compounds there that have ions sorbed to them, and they when water with other ions dissolved in it come into contact with this stuff, there's a competition between the ions that are dissolved and the ions that are sorbed, and the ions that you want to remove it's designed, these resins are designed so that the ions that you want to remove can outcompete the ions that are already sorbed onto this stuff. So often if you want to get calcium out, you have a resin that has sodium sorbed to it. When the calcium comes in contact, calcium-bearing solution comes in contact with this stuff, then the calcium boots off a sodium that's sorbed to the surface, and so calcium is removed and sodium is added instead. So you have kind of a exchange there. And in other cases, here's a mineralized vein, so we've got precipitation in the solids of the porous media adjacent to a fracture. This chemical analyses using gas chromatographs also make use of fluid and solid reactions to characterize composition of various compounds. So a couple of weeks ago we looked at homogeneous reactions, and they're reactions that take place in bulk materials and basically bulk fluid, so involve mixing within the bulk fluid like we showed here. And what we're going to do now is look at these guys, interactions between stuff that's dissolved in fluid and has a reaction that takes place on this solid surface. Okay, so there are a variety of things that would fall into this category. Sorption is one of them, and the simplest way to think about this is that we've got some kind of an ion here, and it's in solution, and it goes and interacts with the surface and sticks to it. So it's still a sodium ion. It's just stuck to the surface with some kind of electrostatic force, perhaps, and then it's immobilized there. And something happens, and it can come off of the surface, but it's not really undergoing much of a change. And so we could have something similar with precipitation, where we've got some ions in solution, and then they form some kind of a solid phase precipitate on the surface. So they're actually changing phase to some other chemical compound. And one thing that could happen with precipitation is that, if we just think of this at first, we have stuff precipitating here, and early on it doesn't really alter the surface much, so we can think about this process in just kind of a baseline way. But of course, as this progresses, then the precipitate starts to, and that's what I'm showing here, starts to build up, and instead of having interactions between this guy in solution and this surface, the precipitate gets to be thick enough so that it's really obscuring the stuff in solution from the solid surface. And then you have then things are going to change, because then you have this guy in solution really interacting with other precipitate. Okay, so that can cause some interesting effects. And one of them would be clogging. So if we have enough precipitation that it creates a change in the geometry of a pore, for example, basically if it just is thick enough so that it changes the geometry of the flow of the water over it, then there'll be an interaction between the precipitation process and the flow that is probably bringing constituents to the surface, and that can build up in porous media, for example, or in conduits. You can have this layer build up enough so that it clogs up pores, and so obviously that creation of a significant thickness of precipitates would be a problem. Well, it could be a problem if you want to induce flow. It could be actually something that you're trying to do. And I guess the kind of the flip side of precipitation would be dissolution, where you've got some compounds here, some molecules that are well, you've got a solid phase here and some kind of reaction occurs so that the molecules or the atoms that are forming the solid phase end up then in solution, and there you've got a change in the solid surface, and again you could have a small amount of this occurring just as a dissolution process that it might actually look like desorption. But you could also have then enough of this occurring so that it changes the solid surface, changes the flow, and a feedback that causes then some fairly interesting behavior. And so I guess what I had in mind with this is that we're really just thinking about chemical reactions, so dissolution and precipitation of chemicals, but microbes are also involved in this, and you can have microbes forming a film or a layer of microbial material on surfaces, and that can be a site where a variety of important chemical reactions take place, and you can have a buildup of thickness of material, an increase in the thickness that is also something that would contribute to clogging. So in some ways similar to these chemical effects, but involves biochemical and biological processes. And so all of this stuff really is things that are happening at the surface, at the fluid solid surface, but we can also have this process, matrix diffusion, where we've got some compounds that are in solution here, and they might initially be sorbed right here to the surface, but from a gradient in chemical potential, they can penetrate in and go below the surface from diffusion. So that might also be, matrix diffusion might also be viewed as in this realm of different processes. Okay, so that's an overview, I think, of the things that we might be interested here, and let's see, a conceptual model for how we might go about thinking of this. Well, we've got some kind of concentration, an aqueous concentration up here in the fluid, and we've got a concentration of these species here on the solids, and there's some kind of an exchange between them. There's a reaction that takes place here at this solid surface, and it involves this exchange with the stuff that's in solution. So this reaction may be I mean, the reaction rate, I think, is important to consider. The reaction may be fast, and if so, then the reaction could go to equilibrium quickly, and I mean, by quickly I mean it would go to equilibrium fast relative to the rates of other processes in the system. Okay, or it could be slower, and the reaction rate could be slow relative to other processes. And the difference would be, in one case, we would need to consider the rate of the reaction. The other, we could just assume that it's fast enough so that it goes right to an equilibrium condition. Okay, so there'll be several different types of concentrations here that we'll want to just keep in mind. One is the concentration of water, in water, and this would just be an aqueous concentration, and we can do this a couple of ways: mass per volume, so milligrams per liter, for example. And also, you see this done with molar concentrations, so moles per volume of water, or moles per mass. In soils, we typically do this like so. So if you've got a compound mixed in a soil, then the concentration is typically expressed in terms of the mass of the compound. That should just be that should say mass of the compound. So mass of the thing we're interested in per mass of soil. So this would be a basis of mass per mass. And then we also will have a surface concentration. So we've got some surface here, and we've got some stuff sticking to the surface there. And so we would then have a concentration that would be mass that's on the surface per surface area. Okay, so here we're normalizing to a volume, to a mass, and to an area. Okay, so we've got these two kind of end-member concepts of fast reaction rates relative to transport, and in this case it goes to equilibrium quickly, and for this scenario we would be interested in just looking at what we'll think of as the partitioning between the fluid and the solid, the relative concentrations of the fluid and the solid at equilibrium. And there'll be several ways of considering that. If the reaction rate, though, is slow or similar to transport, then we can't really assume equilibrium, and we need to evaluate the reaction rate. And so the way we'll do that is to have a reaction rate. So if the CS is the concentration on the solid, we'll have the rate of change of the concentration of the solid be some function of the concentration in the fluid and the concentration in the solid, and perhaps some other stuff. And this then ends up, this is the same form that we used for reactions, for these homogeneous reactions. We've got the same kind of time scales for this, at least for like a first order reaction, 1 over the rate constant. The diffusion time scale is given by that, and advection time scale just really is a travel time over a characteristic length. And so last time we saw these Damkohler numbers, we can think of the basically evaluating reaction rates in terms of Damkohler numbers. And so if we want to say, well, is this reaction fast or slow compared to other things going on, well, this is a way that might make sense to do it, where this Damkohler of the first Damkohler number, we're comparing the time scale for the reaction rate to the advective time scale, and here to the diffusive time scale. And so this would allow us to make a relative evaluation of the rates and find out which of these rates might be limiting the overall process.
So what's the difference between the first and second?
This and this?
Yeah.
So this one is the reaction rate scaled to the advective rate. So this is how fast reactions take place relative to the rate of advection in the problem. So you might have, say you have a column and you've got flow over length L and some velocity, then and some reaction taking place here. Then based on these different terms, you come up with this Damkohler number. And if it's much greater than 1, then the reaction is fast relative to advection. If it's much less than 1, then it's slow. And so this would allow you to evaluate what process is limiting the rates, limiting the reaction rates. If this is small, if the Damkohler number is small, then the reaction is slow compared to advection, and you probably need to consider it as a kinetic process. Okay, so a lot of processes that we're interested in groundwater, for example, where the flows are pretty slow, end up being equilibrium process. And so we can just, we're not really worried about the kinetics, and we just assume that the mass that's in the water and the mass that's sorbed are in equilibrium. And so the way we can visualize that is an experiment. We can have a batch experiment here where we put some solution with some kind of dissolved mass. I guess I've been calling that CF. And we put some solid in there, and the mass then sorbs to that solid. We shake it up, and we measure the concentration a couple times, and it goes to equilibrium. This concentration in the fluid decreases as the stuff gets sorbed to the solid. You get the change in the concentration of the fluid. That gives you the change, or that gives you the concentration that's on the solid. And you do this several times for different initial concentrations in the fluid. So you start off with low concentration, measure the concentration that's sorbed, and it's right there. You get a point like that. You bump up the concentration in the water. That gives you a higher concentration that's sorbed. And what you find when you do this, particularly at low concentrations, is you often have this linear relationship between the concentration that's sorbed and the concentration that's dissolved in the water. So the slope of this line is the distribution coefficient, KD, and it relates the concentrations that's sorbed to the concentrations that's dissolved. And so this is a linear isotherm, and this is the simplest way to describe sorption. Now, it turns out this works pretty well for a variety of compounds at low concentrations that if you give it long enough to equilibrate. I think, though, you can easily visualize, and I guess that what I'm showing here with this graphic is that here are the solids, and so long as these compounds here that are dissolved are sticking to the surface, there will be what's happening is this guy comes onto the surface and finds a site on the surface that is favorable for it to stick to, and so there will be a finite number of those sites And so this linear relationship between the concentration absorbed and the concentration in the water, it's only going to behave this way so long as there are plenty of sites for sorption for these guys in solution to make use of. Eventually, once you get up here to high concentrations in the water, there will be enough compounds in the water to really fill up all of the sites that are available and for sorption. And then once that happens, as you bump the concentration up in the water, you're gonna get fewer and fewer of the molecules sorbed onto the surface. So this relationship here works nicely at low concentrations, but as you bump up the concentrations, you find that down here is linear, but as you bump it up, you find that it rolls over like this. So as we increase the concentration of the water, the increase in the concentration sorbed gets less than what we would expect if we were to extrapolate this out. And eventually, it might actually just level out, and you would have all the sites filled. So this kind of site model gives rise to nonlinear isotherms, and there are several that have been proposed. One of them is the Freundlich isotherm, and it's relating CS here to C using this power function. And so for a shape that looks like this, you'd have an exponent that was less than 1. And something like this, though, it never really levels out, right? If it's a power function, it's going to go like this, but it's going to keep on increasing. Langmuir isotherm, though, it will go and level out. This is the Langmuir isotherm, and you can see as C gets big, so as C times alpha, if that gets much bigger than 1, then the denominator is essentially just C times alpha. And so for C, for C much greater than alpha, then CS goes to beta. Okay, so for C very much greater than C alpha, I'm sorry, let's write it like this. For C alpha much greater than 1, then CS goes to beta. Okay, so this would be beta here. All right, so that's another way to describe equilibrium sorption. There's no time involved here, but it allows us to go up to high concentrations. All right, so if we want to go and do an analysis of this, one way to visualize it is that we've got flow through porous media, and we've got a concentration in the fluid and a concentration in the solid. And so we have two domains. So here would be a source, and we're having flow go in this direction. And this is the fluid. Well, there's fluid concentration and solid concentration. Okay, and what I'm doing is showing these as two different domains. When I do this in PowerPoint, I've got an animation that takes this guy and just puts it right over top of it. Because the way to visualize this is that there are two domains, but they're overlapping domains. So they exist in the same place. And what it means is that this point right here, spatially, you could go there, and that's the fluid concentration, and then I come down here, and that's the same location as this one in the coordinates, and this would be the sorbed concentration at that point in the model. So they're overlapping. Here's another way to think about it, that we've got, we really have something like this where you've got concentration in the fluid space and concentration sorbed, and we can think of that as this space modeling the concentration in the fluid and this space modeling the concentration in the solid, and they're really overlapping. Okay, so we think about that, and then we can just have this relationship here, or even this one, Langmuir with competition, that allows us to go from one to the other, from one of these domains to the other domain. Okay, so that would be one way to think about it. If we go and do a little pulse test, where we've got a little source of mass there, and we've got flow like this, then this is showing it at increasing time like that, and you can see that it's starting to, this little pulse is moving downstream and spreading out as it goes. And so what's happening here then is that this is showing these plots show essentially the concentration of the dissolved phase and the concentration that's sorbed. The plots would be the same. The scales would be different because there would be some there would be different units, and the magnitudes would be different, but the pattern would be the same, because as the mass is moving through the water, it's instantly equilibrating with the solids. Okay, so we could keep track of both, and we could have two different sets of maps with similar patterns, and in different units. What happens then is that what I'm showing here would be a monitoring point down here. Actually, I guess at several different points downstream, and you can see we put in a pulse, and as we go further downstream, the peak spreads out, and the peak diminishes, and it spreads out. If we don't have any degradation, then if we were to integrate under this peak and integrate under the under this curve and integrate, well, we would integrate under this curve, and we'd also have to integrate the sorbed mass, but we should be able to keep track of all of the mass in this scenario. Okay, so one of the things that we could do with this is use this to calculate the linear flow velocity, as well as the porosity and the retardation factor. So if we have a pulse that's released up here, and we measure it at this point, and then measure at this point, then we would get a pulse like that and a pulse like that at these two different locations. So that would be that location, that would be that location. And we can go calculate the first moment, and that would be like the arrival of the center of mass there, and the first moment would be something like that there. And so that gives us an elapsed time. And we need to have this first moment type analysis if we want to get an elapsed time from here to here, because if we have this this kind of broad pulse, then if we want to get a travel time, then it's hard to decide just what time we should use. So the first moment ends up being a good way to do it, and so this gives us the travel time. We have a distance, and so if we have a tracer that is conservative, that's not undergoing any sorption, then we can use the distance and the elapsed time to get a velocity. So I did this and came up with these guys in these are some of the data that I made, that I measured, came up with a velocity of 0.032 with that distance and this arrival time from the first moment. Okay, now the effective porosity, this is something that scales the velocity, the fluid flow velocity in a porous media to the flux. So usually when we're working with porous media, we're thinking in terms of volumetric flux, but for arrivals and for transport like this, then we have the velocity. The relationship between the flux and the velocity is the ratio of the flux and the velocity is the effective porosity. So if we can calculate the velocity this way, then we can we specified the flux in this problem, and then we can take the ratio of these two and calculate the effective porosity. So I did this and came up with 0.31. The porosity that was specified in the model was 0.3, so that ends up working out as just a check that everything's working well. Now we can also do this and calculate the retardation factor. The retardation factor is the travel time, or basically it's the velocity of water divided by the velocity of a compound undergoing sorption. And the sorption is going to slow the compound down, so the ratio of these velocities, it will be greater than 1. And we can do this with a test like this by essentially repeating it. We include sorption, and we get 2 more pulses like this at these 2 different locations, and they're going to look something like this. There'll be instead of this blue one, if we have sorption, then the sorption will cause a delay in the arrival. So we would have a pulse that is like that. It's delayed, and then we'd also have a delay at this one. So we repeat this process of calculating the velocity using a compound that undergoes sorption. That gives us the velocity of that plume or that pulse. It's going to be slower than the velocity of the water, and we take the ratio of those two and determine the retardation factor. Okay, so I went through this and came up with this lag velocity that gives us a retardation factor of 2.3. Okay, so this ends up being a kind of a nice exercise that shows the effects of sorption on velocities, and this will be one of the things that we'll go through with the exercises that we're going to do with the analysis. All right, so let's see how to include this in the governing equations that we've been doing. So this is going to be a porous media analysis. So the thing that we'll be interested in conserving is the mass, and this then little c it'll be mass per total volume. But because this is in a porous media and concentration C, a big C that we use is done on a per fluid basis, then little c is going to be concentration times porosity. So it's mass of the compound per volume of fluid, and porosity is volume of fluid times total volume. Okay, so that's going to be the dependent variable, Cn. So our storage term is just the rate of change of Cn with time. Advection is just volumetric flux times C, and we've got diffusion and dispersion. So these are the same as we had last time. What's going to differ now is S. And so we're going to think of sorption as a reaction that removes mass from the fluid that's from the fluid in solution. So if we just take a look at the concentration that's dissolved, the sorption will remove mass from that. So, and it will be distributed through the domain, so it'll be it'll work like a source. And the rate of change of the concentration in solution is going to be equal to the negative of the rate of change of the concentration that's sorbed. Okay? From if this guy here, this is just a rate of change with time, and if that is due to sorption, then we're going to take this mass, take it from solution, and sorb it onto the solid. So this must be what's happening. And this guy here, that's the bulk density. And that is needed because, remember, we started out with the concentration in solution being different than the concentration that was sorbed. When the concentration is sorbed, at least in the way we were doing it here, we're using a solid phase concentration. So the solid phase concentration, here are the units, mass that we're conserving per mass of soil, and this is all per time, so there's the time. And then this term here, that's the mass of the soil per total volume. Okay, so if we were to take some of this soil, take a chunk of that, take a chunk of the soil, get the volume of it, and then dry it all out and weigh it and get the mass of the solids, that ratio would be this guy. Okay? So that's the bulk density. Yeah.
So porosity is included in that concentration?
This is porosity here.
Okay.
So what we're saying is the source is equal to the rate of change of that with time, and this guy is mass per total volume per time. That's the units of this. When we take aqueous concentration times porosity, we get the mass of the solute per total volume. Okay? So on this side, we have the mass of the solute per total volume per time. And we said conceptually that as the mass of the solute drops, the mass sorbed increases. So there's the negative. And when we relate the rate of change of the sorbed concentration, or the rate of change of the aqueous concentration to the sorbed concentration, we have this change in sign, and then on this side, we basically need to have a rate that has these same units, but is written in terms of the sorbed concentration. Okay? Have to have the same units. And so what then is required is this additional term here. And the way I'm presenting it is we're really just doing this based on a units argument. So what I've done for this term is write out the units, and if we have these units, then I think what we can see is that that cancels and that cancels, and this term here has the unit of the mass of the solute per total volume per time. Okay? So for this equilibrium sorption process, the rate of change of the aqueous concentration times porosity is going to equal the negative of the rate of change of the sorb concentration times the bulk density. Okay? That's really the key thing that we're adding here. All right. So substitute in everything, and all of this stuff is the same that we've had last time and had for a couple of classes. What we get now that's different, though, is this here. So this, and on the right-hand side, this ends up being it's like this reaction term, and it's written in terms of the rate of change of the sorb concentration. Okay, so this is our governing equation, and actually, let me see if I can turn off this. Maybe we won't get interrupted by that thing anymore. Okay, so here we go. This is now the governing equation. The good news is we've got this this term in here that's covering sorption. The bad news is that, you know, we said, well, this is our dependent variable, but this guy here new variables that are changing. So we got to have a way of dealing with that. So here's what we're going to do. So this is what we get when we use our general approach for coming up with governing equations using conservation. What we're going to do is to say we're going to go back and look at those isotherms and say for just a linear isotherm, remember the plot that went like this, the concentration on the solids and the concentration here in the fluid, just linear. So that means that the concentration on the solids is proportional to the concentration of the fluid, right? And so that means that dCs dt, if we just say that Kd is constant, okay? So we can do that. And then let's just say, for make life easier, I mean, most of the time this bulk density, that's constant. So it comes out of this derivative. So let's say the bulk density is constant, the porosity is constant, and let's lump that stuff together and just call it the dispersion. And let's say that the porosity is also uniform. Okay? So the porosity in here, it has to be spatially uniform to come out. But if we do that, then I think that's a pretty reasonable assumption. Then we get this. We get minus, there's the porosity. So there's the dispersion term. And there's the advection term. And then we get plus, I'm going to zoom in a little bit. So we get plus n dc dt. And then that's going to equal minus rho b KD, DC, DT. A little crowded there. But that last term is what we get by taking this, substituting it in there. And okay? So we good with that? All right, so then, this then simplifies our life because now we only have one concentration, just the aqueous concentration, not the solid one. So there's dCdt and there's dCdt. Let's bring those together, and then we get this. Well, that equals 0. Okay, well, the way that this is then usually done, and I'm going to give myself a little more space here, is I'm going to factor out n there. So I write this like this. Okay? Now, if n is constant, then we can divide through, and we get n right there, and n is gone there. Okay? So here's what we get now. We have, this is the dispersion, or this is dispersion, here's advection, and then here's dCdt, and here's this thing. So this thing is called the retardation factor. So that's called R. And we could then write it like this. Let's take a simple case where D is uniform, and so we have minus D over R del squared C, and then we can, if the flow is divergence free, then the Q n comes out, and we get that. And let me do it like this. This is how you usually see it. V over R. Okay? So what I did was to say that V, the velocity, is Q times the effective porosity, which is what we saw on the previous slide. So there's the velocity. And we've divided through now by this retardation factor. Okay, so here's kind of a simplified version of the transport equation with this equilibrium sorption using just a linear isotherm. Okay, so this is often, I don't know, there are a lot of situations that can be simplified to be something similar to that. Okay, but we have made quite a few assumptions to get there. This is that retardation factor that we saw on the previous slide. Okay, and we can see how then the retardation factor for this case relates to these other parameters, the bulk density, KD, and the porosity. Okay, so that's what you get for retardation factor using a linear isotherm. We saw there were other isotherms. We can also do something similar for those cases. And here's an example of that. Here's this Langmuir isotherm where CS is like that. Here's the way that it works. I'll just show you just real quickly. This is the equation that we started with, right, with the dCds, dCs dt on this side. Then if we say it's Langmuir, then we can relate CS to C. We'd take the derivative of CS with respect to T there, and we work it through, and you end up with that for dC dt. Okay, so that then allows us to take this guy, substitute it in there, and you end up with this. So when we did this before, we just got a KD, but now we've got this. It's now a bit messier because we've got this other C in there. But we can go and fiddle around with it and do some algebra, and you get this. So this before was this was those terms, and before we had that stuff, we were just calling KD. But now with this more complicated isotherm, we get this other stuff. The approach was just exactly the same as what we did in the previous slide, but we get this more complicated relation, and it ends up, it's more complicated. I mean, it has this C in it, so that'll make it more complicated to calculate. But at any rate, we can still think of this as a retardation factor, and we can go and write it like that, just like we wrote before. But now the retardation factor is a bit different than the way we define it using a linear isotherm. Okay, so those are some applications for the equilibrium case for where we have the sorption reaction being very fast. And yeah, here's COMSOL format. We can let's skip over that. All right, so now, what if this reaction with the solid is slow? Then, and we need to really look at the reaction explicitly. And so, in this case, here's our conceptual model. If this is slow, then the way to think about this is that we've got this reaction happening here. So we need to consider that, and then we also need to consider fluid flow and transport in the fluid. But the way what's happening then is we have to have the mass transfer of the compounds that are dissolved in this fluid over to the solid surface. So there's this flux that occurs, and we can think about it like this, that we're having mass removed we're having mass consumed by this reaction, and the rate at which the mass is consumed by the chemical reaction is going to be the rate at which mass is supplied from the fluid. So from the fluid's perspective, if there's some reaction going on at the surface, that surface is the boundary for the fluid. And so what the fluid sees is a sink, and it sees the mass going away at the surface. So one of the things that will trigger is diffusion towards that surface, because there will be a drop in the chemical potential as this process takes place. Okay, so that'll get you a mass transfer from the fluid onto the solid surface, and then you have reactions that take place on the solid surface. So here's an example of first order sorption reaction. It's reversible, so you can have the stuff sorb onto the surface and come off of the surface. And it gives you, it's written just as a as a kinetic expression. So the rate of change of the concentration on the surface, it depends on the concentration in the fluid and the concentration on the solid. And we get here a kinetic expression that is very much, well, essentially the same thing that we had for this, for a simple reaction where A goes to B. Okay, and so that's the way to think about how this reaction may take place. We'll have a kinetic reaction here that's expressed like that, and then as that reaction causes mass to be removed, we have a boundary condition on the fluid here, a flux boundary condition that has flux across the, or flux basically out of the fluid domain onto the surface to keep pace with that reaction. Okay, so we can go back to our concept here where we have two domains, a fluid domain and a solid domain. And we've got the way that it usually goes is that we can have mass being transferred by advection in the fluid domain, but in the solid domain it only moves by diffusion. And then we can have some kind of a transfer between the two, but there's, because of the kinetics, the concentration in the solid depends on the concentration in the fluid, but it also depends on the whole concentration history, okay? Because if the reaction is slow, then the concentration on the solid may lag long behind the concentration in the fluid. Okay, and so that means that for this case, well, basically for the equilibrium case, we only really need to analyze the concentration in the fluid, because if it's in equilibrium, we can immediately calculate the concentration on the solids. But for the non-equilibrium case, we have to analyze both, the concentration on the solid and the concentration on the fluid. Okay, so here's a way to think about it. In the mobile phase, we've got an expression that looks like this. So this is pretty much what we did when we just did the mass transfer, or when we just did the mass balance equation. We got dispersion, we got advection, we got rate of change of the mass stored, and then we have this reaction. And there's, see that, there's the CS and there's the C fluid, okay? So in order to solve this, we need to have, we've introduced another dependent variable, CS, so we have to have another equation for the sorbed phase, and this has diffusion on the solid, rate of change, and then this is the reaction on the solid. Okay, and then we have to have some ability to exchange between them. Okay, so this is really the equation setup that we'll be using. One way to do this is to use non-equilibrium sorption kinetics. So we saw a first order equilibrium kinetics. This is first order disequilibrium kinetics. We got similar expressions for langmuir, and a variety of other things. Okay, so this is one way to think about it. Another way to think about it, though, and what I think ends up being more productive, this actually will work if you just have like one species that you're interested in. But if you have multiple species, then a good way to think about this is using the kinetics expressions that we saw last time. And just instead of picking out this Langmuir kinetics, you can write out the reactions between the sorbed phase and the dissolved phase, and write out kinetics expressions for those reactions. So if we're going to be working with this, you might try this at first. This kind of approach would work for fairly simple systems, but there are other systems that I could show you examples of, but we probably won't get to today, where you'll want to consider more broad reactions. But let's just see one of the consequences of having this disequilibrium sorption going on during a pulse test. So here's the pulse, and it travels downstream and spreads out. So the concentration here, the aqueous concentration, it looks quite similar to the concentrations that we saw for the equilibrium sorption. But the difference is that what I'm showing here with these contour lines, these are the concentrations that are sorbed. And what happens is when there's when it's not equilibrium, then when you have kinetic sorption, then the sorption the concentrations don't need to be equal. And so what happens then is, for this setup, you as this pulse moves on down, it sorbs onto the solids, and then it desorbs more slowly. And so you're ending up here with it's like a plume that's left behind on the solid phase, and so it's a low concentration, but it's kind of a relic of the dissolved phase moving through that area. And when you look at the concentrations, when you look at the breakthrough curves, you see that kind of effect shown here. So this is showing the breakthrough curves of the pulse at two different, basically just two different scales. So the concentration here on the water, and so the concentration goes up and then down as the pulse goes through. But for this case, where we don't have equilibrium, we have a kinetic sorption, then the concentration on the solid increases here as the concentration in the water increases. But then when the concentration in the water decreases, the concentration in the solid here, I did two cases. One, the red one, where it's irreversible. So once the mass is deposited on the solid, it can't come off. And then the black is reversible but slow. So this is the black dashed line is the concentration on the solid that results from this pulse coming through. The concentration goes up, and then it decreases more slowly. So in some ways, it's behaving like matrix diffusion does. And this is what it looks like when we have this is just showing the results in a different scale. Okay. So there are a variety of other interesting processes. One is competition between different ions or different compounds for sorption sites. And the idea here is that you have a solid surface with these little cutouts right here are different sorption sites. And some compounds fit in those sorption sites well and are strongly bonded. Other compounds will become sorbed, but the bonding between the compound and the sorption site is much weaker. And so in that case, you can have competition where some compounds are sorbed, other compounds come along and can boot those compounds off, and so you have then an exchange. And that was what we saw with the ion exchange resin. So that becomes a pretty interesting process, because you can have some things showing up in solution that you didn't realize were there, and other effects. And so we have some examples about that. Another example that is interesting is where we have this reaction that creates enough mass to build up and start to clog up the pores. And so in this case, we go through a kinetic expression for the concentration change. But the way to think about it is that if we have a concentration on a surface, we've got a mass per unit area of the surface. If we have that mass, if that mass has some density, then it has some volume per area. And if it has a volume per area, it has to have some thickness. So if we're interested in clogging, what we do is we calculate the concentration per surface area, and we just translate that into a thickness of the sorbed layer. And as that gets thicker, it starts to block the flow potentially and change the flow paths. And then that ends up feeding back into the precipitation process and causing some interesting effects. And here's some pipes being clogged. Here's some arteries being clogged with plaque. And here's a biofilm that's formed. And here's some cement in pore space where you have a sedimentary rock that's cemented up. So all of these would be reactions that start out as surface reactions and build up so that they have thickness that's great enough to start to obscure the pore, obscure the way that fluid is flowing and providing compounds to this reaction. And so there's this interesting feedback that develops. So that's all the time we have. Some of you will be dealing with these more complicated and more interesting processes, and so we'll hear more about them later on when we hear the presentations.